This is a simple exercise on external force convection analysis. Let's say you have a flat plate of 50 centimeter in length. The plate could be of any material, wood, metal, anything. And you were told that there is air flowing over the flat plate at 3 meters per second. The air being at the surrounding temperature, in this case 25 degrees Celsius. And the flat plate is at 35 degrees C. Now, this is definitely external force convection analysis, flow over a flat plate. First, we have to make our assumptions before we move on. The first being steady state, because if the flow of air over the flat plate is not steady, then you may not just use the Newton's law of cooling simply. The H would have varied with time. Second assumption would be you assume that is one-dimensional heat transfer from the flat plate to the surrounding air, the flat plate being at a higher temperature than the surrounding air. You assume that there is no axial conduction along the flat plate, and no heat generation in the flat plate nor in the air. And finally, constant thermophysical properties. You may obtain that at the flame temperature. That is, with this assumption, you are assuming that the thermophysical properties along the flat plate during your heat transfer analysis is constant at 30 degrees C. So, the boundary condition type, we know we have force convection, external, over a flat plate with constant temperature stated. You have to find out whether the flow is laminar or turbulent over the flat plate, because the convective heat transfer coefficient is different if the flow is laminar or if the flow is turbulent. So let's have a look. You have your flow. You can determine the Reynolds number, which is velocity multiplied by the characteristic length divided by the kinematic viscosity. In this case, if you are performing your heat transfer analysis over the whole length of the plate, then your characteristic length will be 0.5 meter. And your velocity will be the free stream velocity of 3 meters per second. But what about the kinematic viscosity? Well, you may use the table to obtain the value at the flame temperature. With that, our flame temperature is 30 degrees C. Then you may proceed to obtain the density, the specific heat, thermal conductivity, viscosity, as well as the Prandtl number. Now, let's look at the Reynolds number. It's 9.3 times 10 to the power 4, which is less than 10 to the power 5. Therefore, we said the flow is laminar. Please take note that in this case, we are assuming that at 10 to the power 5, the flow will start to become turbulent. Yes. What happens if you want to analyze heat transfer at midpoint of the plate, not at the end, but at midpoint? Yes, you can do that. The Reynolds number would be much less than the earlier Reynolds number. And in the case where you have a gentler wind, you may determine the Reynolds number too. Now, in the case when the plate is longer than 50 centimeter, let's say 1 meter, and you would like to know if the flow becomes turbulent at all along the plate, then you have to determine the critical distance, xc, where turbulence starts. Using the equation here, assuming turbulence starts at 10 to the power 5, you can determine the critical length. And you will find that for this particular case, the critical length is 0.536. That is, if your plate is 1 meter in length, at 0.536 meter from the leading edge, the flow of air becomes turbulent. But in our case, in this example, we have only 50 centimeter length of plate, then the flow is laminar over the whole length of the plate. So your heat transfer analysis would be laminar flow over a flat plate with isothermal boundary condition. So, with that information, you may determine the thickness of the velocity boundary layer anywhere along the plate. If it's at the edge, you can put your 0.5 meter here. You may determine your thermal boundary layer and perform the heat transfer analysis using Newton's law of cooling. But to get the average heat transfer coefficient, you need to first get your average Nusselt number. In this case, I've chosen to use the exact solution to the boundary layer equations, the Nusselt number here, and that's equal to the convective heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity. Can you use other correlations beside this exact solution? We shall come to that later. So with the Nusselt number, here you get your velocity boundary layer at 8 mm, which is less than the thermal boundary layer. So the thermal boundary layer is thicker at the end of the plate. The Nusselt number you obtain, substitute that into the equation, and you get your average convective heat transfer coefficient, and consequently you get your heat flux of 75.4 watt per meter squared, because your area is not given here. If the area is given, you may multiply that quantity by the area. Now, if you want to know the total heat transfer from both surfaces, the top and the bottom, then you would have to multiply this number by 2. QED. Quite easily done. Actually, quod erat demonstrandum, which means that which was to be demonstrated has been demonstrated. Okay. Now, earlier I said, can we use any other correlation besides the exact solution? Yes, there is the Ch6 and Ozo correlation, equation 726 in your ebook. Yes. If you have with you available exact solution, in this case, laminar flow over a flat plate under isothermal condition, please use the exact solution. In this particular example, I advise you to also get the average Nusselt number, consequently the average convective heat transfer coefficient, and then the heat transfer, and compare the results you obtain using Ch6 and Ozo correlation with that obtained from the exact solution. Okay, in this case, we have analyzed the laminar flow over a flat plate with constant temperature stated. What happens when the constant heat flux is heating up the plate? The second boundary condition. Can you still use 721 or 726? And at what temperature should get the thermophysical properties? Because now the temperature is not stated, you're only given constant heat flux. Well, you have here a loop. Yeah, this can be done with a simple MATLAB code. You have to first make an initial guess of the average surface temperature, and then calculate the film temperature. Proceed to get the thermophysical properties at the film temperature, and then you determine the average Nusselt number, and consequently the average heat transfer coefficient if you need that. From this equation, you will determine the average surface temperature over the plate. Yeah? And check if the surface temperature is close to the initial first guess that you made. Most probably not. Then you have to move and determine a second better guess of the average surface temperature. So it's a loop. If your determined surface temperature is close to the earlier guess, then you may stop. How about analysis over other bodies, like a flow over a horizontal circular cylinder or flow over horizontal non-circular cylinder, flow over a sphere? No worries. Yes, for flow over circular cylinder, there is the equation. You need to determine the Reynolds number as before, but this time based on hydrodynamic diameter, not the length anymore. Yes, see subscript D here. For a circular cylinder, the hydrodynamic diameter is the diameter of the cylinder. So the C and the index M may be obtained from the table under which condition the flow is. For the flow over non-circular cylinder, you may also use table 7.1 for the relevant correlation. The hydrodynamic diameter would be 4 multiplied by the cross-sectional area divided by the perimeter. And for the sphere, you may use the Whittaker's correlation that's given here. But in all these cases, please make sure at what temperature you should use your thermophysical properties, because some correlations require that you take the thermophysical properties at the film temperature, while others require you to have the thermophysical properties at the free stream temperature. Even for this Whittaker's correlation, you have to get the kinematic viscosity at the surface temperature. Yes. So, for most of these correlations, they are applicable for engineering calculations in practice, but they are not exact. The error can be as large as 25%. So, make sure you understand fully under what conditions these correlations are applicable. Q.